Okay, Chapter 2, Section 7, Combining Functions. In this section, we're going to look at the sums, differences, products, and quotients of functions, composition of functions, and applications of compositions. Okay, so first we're going to look at the sum, difference, products, and quotients of functions. So two functions, f and g, can be combined to form a new function, which we can identify as f plus g, f minus g, f times g, and f divided by g in this way. So this is, I think, commonly a common source of mistakes here. So what we want to do is identify this as a function, and we want to identify g as a function, right? So this could be like 2 plus x, or g could be x squared minus 1, right? Something. It's some sort of a function, and we want to define a new function, which comes as the result of adding those two functions, and then we want to come up with a name for that function. And so the name we assign to it is this, right? It's convenient. That way the name tells you how you achieve it, right? So this is a new function. It just happens to have this as its name. So we can also look at the difference, f minus g, f times g, or f divided by g in a similar manner. Okay, so for example, here we have a function f plus g, right? So this is the name of the function, right? I could have named it, you can name a function f. For example, I could say f of x I could say, for example, f of x is equal to 2x plus 1, right? Or I don't have to use the letter f. I could use the letter w. W of x is equal to 2x plus 1. Same thing, right? It's just a function in x. And so when we get comfortable with this notation, we realize that this letter here is being used as the title of this function, right? The f function. Whereas in this case, I used the letter w. So we can use anything we want there. It's just that it would be a little bit more cumbersome if you use something more complicated, right? If I used something like heart x, it would be a little bit weird to say that the heart is the function, the heart function, 2x plus 1, right? So then I can look up, I can say, what is heart of 3? Okay, well then you would input a 3 into there, and you get 2 times 3 plus 1, right? Okay, so we can name it anything we want. So as long as we're naming it, we could also name it as this. So f plus g is the name of the function evaluated at x, and so all of this kind of stays together. Think of it as the name of the function. So we can later evaluate this function by plugging in a number. F plus g evaluated at 4, for example, means go to the f plus g function, and wherever you see an x, replace it with a 4. So for example, this could be the 2x plus 1 could be defined this way. So this would then be equal to 2 times 4 plus 1. Good. Same thing. Now, it's a little confusing because we have this plus sign, so there's this urge to want to do something with this, like math or something. But remember, it's the title, it's the name of this function. We just happen to name it this way so that people can remember what its roots are. It's kind of like when you have a kid and you give it, the last name of one parent and the last name of the other parent, so you know where that kid came from. But it's still just the name, right? So this just helps you identify where it comes from. So it is equivalent to the sum of f of x plus g of x, right? So this is one function, and then the f is another function, and then let's put it in green, and then the g is another function, right? So you have one function, g of x, you have another function, f of x, and if we add them together, that will be this new function, which we can call anything we want. We could have called this w of x if we wanted to, but if you just called it w of x, you would lose track of where it came from. So we labeled it f plus g. right? I've seen other authors do something like this in order to kind of have the best of both worlds, where you just label it some letter, so it's just like a function, but then you keep track of where it came from. So I've seen some other authors do the following. They just take this, and then maybe they just like write this right underneath it. That way you remember, oh, it's a function W with the letter W, but they keep track of this little guy down here, so you remember where it came from. Oh, it's this function that's the result of adding the f and the g function together. Okay, so it's a function. The new function f plus g is called the sum of the functions f and g, and its value at x is f of x plus g of x. Of course, the sum of the right-hand side makes sense only if both f of x and g of x are defined. That is, if x belongs to the domain of f and also to the domain of g, right? So the new function, the f plus g, this new function right here can only be defined for values where f of x is defined and also g of x is defined, both. And then it's defined there. If there is an input value that makes this undefined, then that value cannot be part of this new function. Good. So if the domain of f is capital A and the domain of g is capital B, then the domain of the sum function f plus g is the intersection of these domains. That is, A intersect B. Good. So all the values common to both functions, all the values common to both domains of both functions makes up the domain of this new function, which is the sum of the function f plus g. Similarly, same thing for the difference, for the product, for the quotient. It's always going to be the intersection. We just have to be careful that when we're doing the division, remember, we always have to make sure that we don't accidentally divide by 0. So we have to make sure that we exclude any value in the domain of g such that its output is 0, right? So just got to make sure we carefully vet out those values. Okay, so we can put those all into a nice big table here. So let f and g be functions with domains a and b. Then the function a plus g, f minus g, f times g, and f divided by g are defined as follows, right? So remember, don't lose track of the fact that all of these guys on the left-hand side are new functions. This is a new function. We just happen to label it, right? This is part of its name. It's the function f plus g evaluated at x, and it happens to be defined by adding the function f and the function g, right? So that's the connection between the two. And again, same thing for all the other ones. So here, this is a new function, which we happen to identify, title it. This is the name of it, f minus g, like this, in parentheses, right? So you have to be real careful with the notation to be able to distinguish that this is a function evaluated at the variable x. And it's defined to be the difference between the f function minus the g function, right? Pretty straightforward. Same thing with the product. This is a new function, fg like this. This is the name of the function. And this is the input variable x, right? We input x into this new function. This is the name of it. And it happens to be defined as the product of the f function evaluated at x times the g function evaluated at x. And finally, the difference, the quotient, is defined this way, right? So this is the title of this new function, f divided by g, valued at x, and it happens to be defined this way, which is going to be the f function divided by the g function, and it's valid everywhere except whenever the g function is equal to 0, right? We can't divide by 0. Okay, so the domain for all of them is going to be almost identical. It's always going to be the intersection of a and b, where a is the domain of f and b is the domain of g. So it's all the values that will result in a valid output for the f and the g function at the same time. Good. Okay, and then we just have to be careful that the g of x function doesn't have an output equal to 0. Remember, we're not saying, this is another common mistake, we're not saying you're not allowed to input a 0. You're allowed to input a 0 potentially. It's that the output of the g function can't be 0, because then you would be dividing by by 0. Good, good, good. Okay, let's look at some examples. So, for example, let's take a look at this one. Let f of x equal to 1 over x minus 2, and let g of x equal to the square root of x. Okay, find the functions f plus g, f minus g, f times g, f divided by g, and their domains. Super easy. It's so easy, it's kind of weird, perhaps, because it's so easy, but we'll get through it. What just happened? Oh, highlighter. Okay, so let's define them all. So the new function, this is a new function f plus g evaluated at x. And the definition of this new function is that it's equal to, in fact, the sum of f of x plus g of x. Good. And so f of x is exactly this, so that's just going to be equal to 1 over x minus 2. And g of x is just equal to root 2. Oops, sorry, root x. And that's it. So this is a new function, f plus g, evaluated at x. And it's this, right? But if I labeled it something else, no, right? If I had labeled it w of x equals to 1 over x minus 2 plus root x, then we would lose track of where it came from, right? We would know that this w function is the result of adding the f and the g function. So for that reason, we adopt this idea of labeling it with this kind of a weird notation of f plus g evaluated at x. Now we could, we could simplify this, combine like terms, bring them together, and that's fine. But that's not really the point of this exercise. We just want to show what the sum is, which is pretty obvious, just to glue them together, add them together. Let's do the other one. So that one is the sum. We also have the difference. So now we have this new function, which is going to be f minus g evaluated at x. By definition, that's going to be f of x minus g of x, which then is equal to 1 over x minus 2 minus root x, right? And so this is a new function, f minus g evaluated at x. This is the new function. Next, we have the product. So here is f times g evaluated at x, again defined technically as f of x times root x, g of x. Jump the gun there, g of x. And so that means that this new function is equal to 1 over x minus 2 times root x. And then since we can just put a little 1 underneath here, it's really just root x divided by this. Same thing as root x divided by x minus 2. Good. Last one. We have that f divided by g evaluated at x is equal to f of x divided by g of x, which in this case is going to be equal to 1 over x minus 2, that's up in the numerator, and all of that gets divided by root x, and that's my new function, f over g evaluated at x. Right, so in each one of these cases, we have 4 unique functions that we've identified, and I'm not going to bother to simplify them, but I think the point is made of how you would arrive at these new functions. So that's this one and this one. Okay, these functions and their domains. So let's think about the domains of each one of these. What's the domain of this one? Well, as long as we want to stick to the real numbers, right? By default, if nothing else is said, we want to stick to the real numbers. So the real numbers for each one of these. So for this one, the domain of this guy is x. Domain is x such that x is greater than or equal to 0, right? You're allowed to have anything that's positive, because it's a square root. Anything that's positive or 0 is okay. And then the domain of this one is going to be all real numbers except x cannot be equal to 2. Right? So x such that, and then the only restriction we have is that x cannot be equal to 2. So I have the domain of this function, the domain of that function, so I can bring them together. So when I bring them together, the intersection of these two, all the things that they have in common, is going to be all positive numbers, except we're going to have to skip the 2. Good. And that's going to be the same thing for this one. So both of these have the same domain. Domain is going to be equal to all real numbers such that x is greater than or equal to 0. So that includes a 0 is allowed there. A 0 is allowed there as well, because then we'd end up with just 1 over negative 2. And that's fine. That's not undefined. But then we also have one more restriction, and that's that x cannot be equal to 2. Right? Because if we let x equal to 2, we'd end up with a 1 over a 0, which is undefined. Okay, so that's the domain for both of those two. What about this one? It's going to be the same domain. You can't have a 2, and that one must be greater than or equal to 0. So that thing is fine. So it's the same domain for this one, it's the same domain for that one, and it's going to be the same domain for that one. What about this one? Well, we have almost the same domain, almost identical. Let's put it in green. For this last one, we also have to introduce one more criteria, and that's that when x equals to 0, square root of 0 is allowed, but you would be dividing, you would have a fraction where the denominator is 0, and therefore that would be undefined. So for this last one, the domain is very similar. Domain equals to x such that x is strictly greater than 0, and x does not equal to 2. So the only difference between the two domains is that this one does allow 0. 0 is allowed for this function, and this function. All three of those, 0 is allowed. But for this one, 0 is not allowed. Okay, let's see how the author organized that. Probably better than me. The domain of f is x does not equal to 2. The domain of g is x is greater than or equal to 0. The intersection of the domains is going to be greater than 0 except the 2. And then we can also use interval notation, which is this. And then just to add one more layer of fun here, we can also draw it using a number line. So here we have -1, here is 0, here is 1, here is 2, here is 3, here is 4, dot, 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 dot. Positive infinity that way, dot, 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 negative infinity that way. Okay, so the domain is all numbers greater than or equal to 0. Let's put it in blue. So we have a bracket there. That means we include the 0, so a bracket there. And then that goes all the way up to the 2, so we can put a parentheses there, like this. So everything between 0 and 2 is allowed, and then another parentheses there. So this is just indicating that the 2 is not allowed. Kind of an ugly way of putting it. So let's use the circle thing. -1, 0, 1, 2, 3, 4, dot, 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 dot. Okay, so another popular illustration is to use the circles. So we want a closed circle at 0, and then we want an open circle at 2, and then we want to draw in everything in there, and then everything out there. There. So here's a graphical description of our domain. And it's going to be the same domain for part A, part B, and part C. All of them have the same domain. Same domain, same domain, same domain, except, notably, the only difference is that this guy does not have the equal sign underneath, right? So in all the first three cases, x is allowed to be 0. No problem having the square root of 0. Square root of 0. It's just 0. No problems there. It only causes a problem here because we end up getting the square root of 0 in the denominator. Okay, so that's the description of the functions. Again, just the most common mistake people have is this weird, admittedly weird style of notation, which is a new function, right? So this is a new function. It happens to equal this because the name is done in a way to describe for you how where that function comes from, right? So there's a new function. Here's a description of the function, and here's its domain. Here's a new function, and then this is where it comes from. This is how it's defined, and then this is the function. Here's the new function, and here's a new function, right? So just don't lose track of the fact that this style of notation is indicating that this is a new function. This is the name of our function. Okay, so part B also said evaluate each one of these at 4. So let's evaluate each one of these guys at 4. So evaluating the f plus g function at x, well, that would be this guy here, and it's equal to 1 over blank minus 2 plus square root of blank. Right? So if we plug in a 4 there, 4 there, 4 there, then we would end up with this is equal to 1/2 plus the square root of 4, which is 2, which gives you 2.5 as a mixed number, 2.5 as a mixed number, which then equals to 5 over 2 as a fraction. So there, that's f plus g evaluated at 4. And then f minus g, f minus g is defined as 1 over blank minus 2 minus the square root of blank. And so if we're evaluating this at 4, right, it's a function evaluated at x, just following this little set of instructions here. So this would be equal to 4, and put a 4 there. So then this is equal to 1/2 minus 2, and 1/2 minus 2 is equal to negative 1/2, negative 1.5 as a mixed number, which is equal to negative 3 over 2. So that's f minus g evaluated at 4. Right, just following along this set of instructions right in here. And then I can do the others. So now let's do the product. So the product is f times g evaluated at blank. And so that's going to be equal to square root of blank divided by blank minus 2. And we're inputting a 4. 4 goes there, 4 goes there, 4 goes there. So we end up with 2 divided by 2 equals to 1. So that's f times g evaluated at 4. It's going to be equal to 1. And finally, f divided by g at blank equals 2. Now, I wrote it as, well, you know, I should just simplify this a little bit, right? Just like we saw earlier, this is going to be the numerator times the reciprocal of the denominator. You can always put a little 1 underneath the root x. And so I end up with 1 over x minus 2 times 1 over root x. So this is going to be equal to 1 over blank minus 2 times 1 over root of blank. And so we're going to put a 4 there, a 4 there, and a 4 there. And so we end up with f divided by g evaluated at 4 is equal to 1/2 times 1/2, which is equal to 1/4. Okay, so that's the result of this new function evaluated at 4. Here's the result of the new function evaluated at 4. Here's the result of this function evaluated at 4. And here's the result of this function evaluated at 4. Zoom out. Okay, so this function, f plus g of x, is defined to be this. This function, f minus g at x, is defined to be this. And so when I want to evaluate it, here's my function, f of x, evaluated at 4. I get this result by plugging in a 4 into each of those values, into each value of x. Same thing with the other ones. So here is my new function, fg. Here is what it equals. It equals to root x over x minus 2. And so to evaluate it at 4, I just have to replace every one of those x values with a 4, and so I get this as an answer. Finally, here's my new function, f of x, f divided by g of x, and so it equals to this, which I could simplify to be equal to this. And then in order to find the value of that function evaluated at 4, all we have to do is replace the x with a 4, and here is our result. So here's the other function evaluated, you get that. So here's what the author wrote. It's a little neater. So same answers. Okay, the graph of a function f plus g can be obtained from a graph of f and g by graphing addition. By graphical addition. This means that we add the corresponding y coordinates. So for example, let's say that we have a g of x function defined by this blue line, and we have an f of x function defined by this red line, and we wanted to add them together and find the graph of the result of this new function, which comes from adding them together. And so we have this one is our g of x, we have this red one is our f of x, and we want to know, well, what would the graph of f plus g, this new function, be if, of course, this is defined to be f of x plus g of x. Okay, so what we have to do is think about the resulting function that's going to come from a point-by-point basis. So we use x way too much. So let's say a is in the domain of this function. So given a is in the domain of this new function f plus g. So that means that it must be a value in the domain of f, and it must also be a value in the domain of g. From the picture, it looks like, well, it must be something in this region, right? So it looks like both functions are defined from 0 up to whatever that value is. Okay, so a must be somewhere in there. So let's say arbitrarily, just for the sake of the picture, let's say that this is a in there. Right? A is definitely in the domain of f of x, and it's also in the domain of g of x, right? Pictorially, it looks like it is. Okay, so that means that this little dot right there on the red line, that would be the ordered pair. That would be the ordered pair a comma f evaluated at a. Which means that this height right there, this height would be the height f of a. Right, which would kind of translate over here to height f of a. Okay, well, likewise, let's go with purple. Likewise, we can have another point right over there. This one would be the ordered pair a comma g of a. Would be that ordered pair right there. And its height from there all the way down to here, this height right there, would be the height g of a, which would track all the way there to some g of a. Okay, so now if we take this little section right in here, this height, which is the f of a, and we add it to the top of this one, so if we add this height, which is the g of a, and we add to it a height equivalent to this one right here. So we kind of measure it, we take it, and we bring it right above. Then that means that this would be the new height. Let's see if orange looks okay. This would be the new height, which would be a height which would include both. It would be a new height which would include both the f of a, which is that green part, plus the g of a, which is the purple part. Right? So this would be the new height of my new function. This would be f plus g evaluated at a. So on a point-by-point basis, I'd have to think about what it would look like when I take the red one and add it to the blue one. Right? Okay, so let's just kind of loosely go through that. What would it look like? So here, I would just add 0 to the blue one. Right? So I start with the blue one and I kind of add the red one to it. And then as I move forward, I'm always adding a little bit. So it's growing kind of maybe like that. And then as we move past that, I'm still adding, but I'm adding a little less to the blue one. Right? If this red line ever came down and equaled 0, then this gold one would touch the blue line, because then we wouldn't be adding anything to it. But we're always adding a little bit to it, so it just comes up and curves down a little bit, and then it comes back up, and then it curves back down a little bit. Right, where here, this is where I've added the most, right? So the gold one will be at the tallest here, because I've added the most to the blue line, and then I'm adding a little less to the blue line. Okay, so roughly speaking, that would be my guess for the function f plus g evaluated at x. All right, hopefully that made sense. Here's another description of that. So this height from here to here is what they're defining as g of x. And then this height from there to there is what they're defining as f of x. And then if you take this little blue guy here, this guy, and you add it to the top of the yellow one, you end up with this guy here. And then the whole thing from the x-axis all the way up to the very top then constitutes this new summation of the two. And that's how you get to a new point, which is defined to be a point, so in this case, that in label A would be a point there. And that point, according to this, I use the letter A, and here they're using the letter capital P. So this point there would be the sum of g of p plus f of p, which would be equal to the value of f plus g. Oh, they like it backwards, so let's put it backwards the way they have it. So that point right there would translate across this way to this height. And so that height right there would be equal to the height of f evaluated at p plus g evaluated at p, which is the same thing as f plus g evaluated at p, right? All of those things would translate to that height right there. Okay, so hopefully that makes sense. Okay, moving on to composition of functions. Suppose that f of x equals to square root of x and g of x equals to x squared plus 1. We might find a new function h. We may define a new function h as h of x equals to f of x evaluated at x, right? So what we're doing here is that we are going to evaluate one function at another function, right? Let's spend a little time with that. So pause that for a second. Let's say I had this function named w of x equals to 2x plus 1. Okay, so we've learned that we can evaluate a function at another number, of course. So w of blank blank plus 1. So we can evaluate this at the number 3, for instance, right? So we can evaluate this function. This is the function w, and we defined it as 2x plus 1, right? This is indicating that this is defined as double the input plus 1, right? That's what this means. Double the input plus 1. Right? That's what this translates as. So when the input is 3, we double it and then add 1. So we get a final result here of 6 plus 1 is 7. Okay, we can also evaluate that function at another letter, as we later learned. So we can evaluate w at the letter, I don't know, how about q? Right? So then all we'd have to do is replace all those x's by a q. So this would be twice blank plus 1. And so we'd have this. We don't do this too often because it seems kind of silly. We had w of x equals this, so now we have w of q equals this. So really we just change the input variable, right? So it doesn't have to be x. It could be any letter at all. It's the concept that makes sense, not the actual letter. Either way, you're still describing the function in the same way. The input, you double the input, plus 1. Okay, so we can define a function this way. We can evaluate it at a number. We can evaluate it at another letter. And then later we learned that we can evaluate it at a little equation, right? So like I can evaluate this at the a plus b. And so I could have 2 times a plus b plus 1. A plus b plus 1. And then maybe simplify it and say that this is equal to 2a plus 2b plus 1. That would be w of a plus b. A plus b. Okay, so we can define our function. We can evaluate it at a number. We can evaluate it at another letter. We can evaluate it at a little equation. And now we're graduating to say that we can evaluate this at another function. So given that, say, this function is defined this way, x squared plus 1, right, I can still stick to my little w, and I can say, well, let's say that w is defined as 2 times something plus 1, and that something that I'm going to stick in there is actually the equation x squared plus 1. I can write it that way, or I can also write it this way. I could say, well, it's also defined as g of x. So the little g of x goes inside there. So here, that means we replace the input with this amount. So this would be twice x squared plus 1. Or in here, we would define that as twice g of x plus 1. Okay, so hopefully that made sense. So going back to this case, they've defined the function f as the square root of x. They've defined the function g as x squared plus 1. So the instructions of this, the way we're supposed to interpret these, this is saying the square root of the input, right? Square root of the input. Give me an input, I'm going to take the square root of it, that's going to be your output, right? Whereas this one's saying that when you give me an input, I'm going to square the input and add 1. Add 1. Oh, let's not do that. Square the input, then add 1, right? That's this set of instructions compared to this set of instructions. Okay, so we're going to define a new function defined by this h of x, and this is letting me know how I'm going to define my h of x. My h of x is going to be defined as the f function evaluated at the g function. Remember, the outside function f means take the square root of whatever the input is. So we're going to take f of the, we're going to take f of the g of x, which is this function, x squared plus 1. So then that equals f of x squared plus 1. And then we input that into our f function. Good. So with these guys, you want to work from the inside out. And so the inside function is that g of x. That g of x is x squared plus 1. And then you go out to the outer layer, which is the f function, and the f function is the square root of the input. So there's our final result. The h of x function, oh, and this should have been copied along, so this is saying that this is the h of x function, and so this is the h of x function. Right? Once we see it in this form, maybe we lose track of where it came from or how it came about, but hopefully it's clear. So the function h is made up of the functions f and g. So given a number x, we first apply the function g to it, then we apply the function f to it. Right? So in this case, f is the rule take the square root, g is the rule square then add 1, and h is the rule square then add 1, then take the square root. Right? So that's the function h. Take the input, square it, add 1, and then take the square root of the whole thing. So we can define or we can describe these composition functions. Oh, they're called composition functions using these kinds of diagrams. So the input is going to be here, right? So the input goes into the g function. Remember, let me write it over here. It was f of g of x. That was h of x. So we're going to start by inputting something into there. That's where the input goes. And then we're going to get an output for the g of x function. That gives you some output. And then that gets plugged into the input of the f function. Right? So the output of the g function becomes the input of the f function. So this is the new input of the f function. And then the f function pops out the output of the f function. Right, so that's what we're doing. And then this diagram kind of describes that. The input comes in, some x input value in the domain of g comes in to under the influence of the g, and then whatever operations the g does, right? So the g could square, add 1, it could take the cube root, divide by 7, whatever the g function is defined to be. In this case, that's what it does. It squares it and adds 1, so that's the output of the g function. And then that output becomes the input of the f function. And then we apply whatever definition the f does, right? In this case, it takes the square root, but it could do anything else as defined by the f function. And so here becomes our output. So just the blue by itself, here's the input, here's the output. Just the purple by itself, whatever input comes here, the output is just to take the square root. But together, combined, we call this a function machine. We have our input for the combined function, the composition function of f composed with g. Right, this is the new function h of x. And the input to this h function goes here, and then lots of math, and then here comes the output to the h function. Okay, so hopefully that made a little bit of sense. In order for all this to work out, we need this to work out in two different places. First of all, when you choose an input, it has to be an input that's in the domain of g. Right? That's number one. We can't choose a value that's outside of the domain of g, otherwise we'll get an undefined to begin with. Then, once we get an output for G, it must also be true that the output of G is also in the domain of F, right? That this output is allowed to be plugged into the F, right? Like maybe the way F is written, maybe F is not allowed to have a 2. Well, you can't have an output that leads to 2 because then you try and plug it in here and F doesn't like 2, so you might have a problem. So there's a couple of places where this whole thing could break down, right? At the very, very beginning, and then also in this middle step where we need the output of the G function to be in the domain of the F function. So in general, given two functions, f and g, we start with the number x in the domain of g and find its image, right? The output is also known as the image of g of x, image g of x. If this number g of x is in the domain of f, we can then calculate the value of f composed with g of x. The result is a new function, h of x, which is defined this way, and is obtained by substituting g into f. This is called the composition, right? Okay. So the result is this new function, h of x equal to f composed with g of x, that is obtained by substituting g into f. It is called the composition or the composite of f and g, and is denoted with this. So we're introducing this new style of notation where this is equal to this composition, right? It almost looks like a multiplication, and it often gets confused with that, but it's not. It's like a little open circle, right? So if we had f times a little closed dot g like this, this one means that you multiply them together. We get the f of x, we multiply it with the g of x, right? That's multiplication. Here we have this little open circle like that, and I'm exaggerating it, but it's a little open circle like that, and it means that we're going to have f, and then we're going to plug into it the g of x, right? So notice how this is going to go in this direction, right? We start off with the g, and then we plug that into the f. Right? So it kind of goes in this direction. All right, moving on. So composition of functions. Given two functions, f and g, the composite function f composed with g, also called the composition of f and g, is defined this way. F composed with g of x is equal to f of g of x. Right? So this is really important in this section, this chapter. Again, not to be confused with multiplication of f times g. Okay, so the domain of f composed with g is the set of all x in the domain of g, such that g of x is in the domain of f. In other words, f composed with g of x is defined whenever both g and f composed with g of x are defined. Okay, we can picture f composed with g using an arrow diagram such as this. So what we want to take away from this is that the blue jelly bean here is the domain of the g function. Or values in the domain of the g function. It might not be the entire domain of g, but at least it's the domain appropriate to the composition of the functions. So we start off with inputs to g, and then that leads to outputs over here in the purple. And it's not going to be necessarily all of the outputs of the g function, but at least it's all of the outputs such that those outputs happen to be in the domain of the f function and lead over to our final destination, right? So in terms of flights, you can think of this as a stopover, right? So let's say that I want to do a connection between two different airlines. I want to connect using Delta Airlines, and then I want to make some other connection using United Airlines. So I must start somewhere where Delta takes off from, right? I can't start off my trip in a city where Delta doesn't operate. It's not in the domain of the output flights of Delta. So I have to start off in one of the cities, not necessarily all of them though, because so I start off at a city that Delta takes off from, and then I land obviously in a city that delta lands in. But now I want that city to also be in the domain of the cities where United takes off from, and then finally end in my final destination. So there could be a couple of problems, right? There could exist a city, which is a perfectly valid delta city, that is in the domain of delta. So this kind of that's extended. It is in here. It is a city in the domain of delta, but maybe it leads to something over here, some output y, that is just not in the domain of the cities where United operates, right? So that would be a flop. That would fail. Likewise, there could be a city, a little over, there could be a city over here, let's call it A. There could be a city A that is a perfectly valid domain of United Airlines, but maybe Delta never goes there. So it's kind of off to the side there, and it just never goes there. What we want is this sweet spot where we want all of the places where the domain of the g function leads to some value in the output function, and then those output functions of the g function, which is delta in my little example, happen to be the ones that are in the domain of the United, and then they lead to your final destination. So all those cities, all those combinations that work make up the domain of my composition function that will get me from the input of this function to the output of the function. Let me write down that example. So for example, let's just assume that letters represent cities. So let's say that G was delta, and let's say that F was United. And let's say that the domain and range are as follows. So let's just assume letters are cities. I don't know what they are. A, B, C, D. So here is the domain of the delta functions. And so this one leads to A, B, C, D, E, F, G, H, I. So my little example, this is Delta Airlines. These are a bunch of cities where they operate from. They can take off from there and they can land in these other cities. And then I have United, and it's got its own domain and range. So there's J. They have their own domain and range, so maybe there's a bit of an overlap. Maybe they have G, H, I, J, K, L. And they lead to M, N, P, Q, R, S. There we go. Okay, so notice that we have a couple of issues if we're setting this up. The letter, if we start off in city A, that leads me to city E, but then E is not over here. It's not in the domain of F. A city, I can start off in city B, and that leads to city F, but again, United doesn't operate out of city F, so that doesn't work out. I can start off with city C, and that leads to G, and then G works out, and then G leads to M. So that is one that will work out. So starting off in C, that will lead me to G, and then I can go from G, and that will lead me to M. So there's one that works out. And then D leads to H, D leads to H, and H leads to N, and then E leads to I, and I leads to P, and then that's it. So these values, A and B, in the domain of G, lead to outputs that are not in the domain of F. So therefore, we exclude them from the domain of the composition. The composition of the two is only going to have these guys. This is going to become the domain of the composition function, C, D, E. And then this becomes the range of the composition function. So let me write that down. So if I have my composition function f composed with g as a function, it's its own little function, it's got its own domain, it's got its own range. And so the only ones we're going to include are these, C, D, E, and M, N, P, right? Because these are the only combinations where this is a valid input of G, right? We can't input W. W is nowhere in the domain of the G function, so we can't input something that's not in the domain of the G function. So we got to start off with the G function, but then it's not the entirety of the domain of the G function. We can only include the ones that are going to work out, and they're going to work out because their outputs are also in the input of the second function, the f function. And so this becomes the domain and range of the composition of functions when we do them in this order. Okay, and so going back to this jelly bean notation, if I was going to do all this with jelly beans, there would be a domain of the G function. It would have these, so it would have A, B, and then it would have a C, D, and E, and then be a little subset there. And this is domain of G, and that would lead to a range of G that has these values. So there's an E and there's an F in there, and then there's this other range values, and there's the G, the H, and the I, G, H, and I. And then there's an overlap. In fact, let me this, where this is the domain of F, and the domain of F has the G, the H, and the I, but it also has a J, a K, and an L, right? And then all of this leads to over here, which is going to end up being the range of F, right? And so we have the M, N, and P, kind of special there. And then we have a Q, R, S are also there. Okay, and so what matters is that now, as far as the composition of function goes, oh wait, let's finish this thing here. So this black outer circle represents the domain of G, and so G leads to all of these guys from this circle to this black circle. Now the blue circle here represents the domain of F, so all of these values get mapped from here over here. And now we're looking at the composition of the functions, and let's put it in green. The composition of functions is going to take just these guys, and it's going to end up with these guys there. And this in green is going to be the composition of F composed with G of X. Right? We start off with values in the domain of G. Now we're only going to focus on these guys because these guys are going to be the ones that map from here to this little group in here, which are the ones that are the overlap of these two sets. And then from here, these are the ones that map to these guys over there. Right? So there's a couple of sources of problems. A and B, city A and city B, are a problem because they lead to cities such that United doesn't take off from there. So they're kind of dead ends. I start off in city A, I go to city E, and then there's no United flights there, right? So there's no United flights there. The domain of F was the cities where United takes off from, and they don't operate out of city E or city F, so they're kind of dead ends. So city A and city B in the domain of G kind of lead to dead ends here. So that's why we don't include them. These cities work well because they lead to cities where United operates. Okay, these cities here, city, city J, K, and L, are a problem because there's no way to get to them. Delta does not fly into those cities. So even though they're valid cities that United can take off from, I can never reach those values, right? If I'm starting off here, there's no way to get to these guys over here. So this is the sweet spot. I can start off in these three cities. They lead me to these three cities. And then those three cities finally lead me to these three cities. So if I just connected them from beginning to end and kind of ignore that middle step there, I can start off in one of these three cities, C, D, and E, and ultimately lead to either this city, M, N, or P, right? So this would be the domain and range of the composition function. Right, so these would be domain and range of the composition functions. Okay, I hope that made sense. Let me highlight this thing. Let's highlight the green. So these guys start off there, and they lead to these middle cities, and then from those middle cities, they lead to my final cities. Okay, so city A and B are a problem because they lead to cities that are not in the domain of F. United doesn't operate out of city E or city F, right? And then cities J, K, and L are a problem because delta doesn't go to those cities, right? You have to start off at a city where where delta can take off from, and also land in a city where United can take off from, right? So we want, going back to the language of this, the domain of the composition of function is going to be all the values that are a proper subset of the domain of the g function, but also happen to have an output of the g function that is in the domain of the f function, so that the final range here is a subset of the range of the f function. I think it's hopefully easier to visualize it than everything I just said, but hopefully that makes sense. Okay, moving on. Let's look at a more mathy example. Okay, so let f of x equal to x squared, let g of x equal to x minus 1. Find the functions f composed with g, g composed with f, and their domains. Okay, so let's think about the domains of each one of these. So what is the domain of x squared? What can I input in here and not have any problems? Well, anything, right? Any number I plug into here, there's no problems. Remember, the only two things we have to look out for is dividing by 0 or taking the square root or the even root of a negative, and that can't happen here. So the domain is all real numbers. Same thing here. You're not going to divide by 0, and you're not going to take the square root of a negative number. So in both cases, so I'd say both f of x and g of x have domains, have the real numbers as a domain. Okay, what's the composition function? So for part A, we have f composed with g of x. So remember, we start off from the right and move this way. So this is f evaluated at g of x, which means that this is f, and then g of x is defined to be this right in here. So that's going to be the x minus 3. And now the f function says whatever the input is, square it. So my final result is going to be this squared. Right? So here this is because the g of x is x minus 3. And then the f function says whatever the input is, square it. So that is going to be f composed with g evaluated at x. F composed with g evaluated at x. Okay, and what's the domain going to be? Again, well, we don't have any problems. No matter what we input, we're not dividing by 0, and we're not taking the square root of a negative number. So the domain of the function f composed with g at x is all the real numbers. Okay, what about this one? We have g composed with f, right? So it's almost the same, except we flip around the g and the f. So this one is defined to be the g evaluated at the f of x, which means that it's the g evaluated at the x squared, which means that we have to take, the g tells you whatever the input is, subtract 3. Take 3 away from whatever the input is. So this one is just going to be that. Right? Again, that's because this is that, right? That's the input there. And so g composed with f of x and g composed with f of x is equal to that. Okay, and just like over here, the domain of this function is also going to be all the real numbers. So the domain of the function g composed with f of x is all the real numbers. Okay, so that's part A. We found f composed with g, and we found g composed with f. All right, so let me circle them. Here's one of them, and here's the other one. Okay, so part B says evaluate f composed with g at 5 and evaluate f composed with g at 7. Okay, so for this one we want f composed with g evaluated at 5, f composed with g evaluated at 5, so that means we're going to take this guy right here, and it's going to be some input minus 3, and then the whole thing gets squared, and that input is going to be a 5, so we put a 5 there, we put a 5 there, and then we just simplify it as best we can. That's going to be 5 minus 3 is going to be 2 squared, so the answer is going to be 4. So f composed with g evaluated at 5 is going to be equal to 4. F composed with g evaluated at 5 equals 4. Okay, on the other hand, they wanted to evaluate g composed with f at 7. So g composed with f evaluated at 7 is going to be this equation. So that's going to be something squared minus 3. And so that something is going to be a 7. So we put a 7 there, a 7 there. And so we'll end up with 49 minus 3, which gives you 46. So g composed with f evaluated at 7 is going to be 46. Okay, let's see what the author did. So f composed with g is the x minus 3 squared, and g composed with f is the x squared minus 3. Both domains are going to be the set of the real numbers. And then when we evaluate them, one of them is 4, the other one is 46, same as before. Remember that in general, f composed with g does not have to be equal to g composed with f. It's allowed to, it can happen, but it's not necessarily true. It's not always going to be the case. So remember that the notation f composed with g means that the function g is applied first and then the f is applied, right? So we start off from the right-hand side. Start off with the g and then apply it to the f function. Whereas the notation g composed with f means that we start off with the f function and then we apply it to the g function second. Right? So again, we start off in this direction. One of the few things in math where we start from the right and go toward the left. Usually it's the other way around, right? Just to add a little extra confusion, that's how we've decided to label these. It is possible to take the composition of 3 or more functions. For instance, the composite function f composed with g composed with f is found by first applying the h to the g. So we start off here and we plug that into the g, and then we take whatever that is and we plug that into the f, and so we end up with this. Right? So we start off with the g of x, that's sort of on the inside, and then that gets applied to this outer one, which is the g1. And then once we finish with that, we apply it to this outer one, right? So it's like an onion where you start peeling it from the inside out. Start off with the with the h, and then plug that into the g, and then plug that into the f. So work your way from the inside out. Here's an example. Let's say we wanted to find this guy. So we have f composed with g composed with h of x. And here are the definitions of the 3 functions. So this one is going to be equal to f evaluated at g evaluated at h of x, which is equal to f evaluated at g evaluated at h, which is this guy, which is x plus 3, which is equal to f, and now the g function says whatever the input is, raise it to the power of 10, where this is the input. So this is going to be x plus 3 raised to the power of 10. And finally, the f function says whatever the input is, do the input divided by the input plus 1. So our final answer is going to be x plus 3 raised to the power of 10 divided by x plus 3 raised to the power of 10 plus 1. Right, so that would be f composed with g composed with h evaluated at x. Okay, let's try another one. How about f composed with h composed with g evaluated at x? See what's that? Okay, so that's going to be f evaluated at at h evaluated at g of x. That'd be f evaluated at h. Okay, so the g is x to the 10th power. Now the h says whatever input, add 3 to it. So this would become f of x to the 10th power plus 3. And finally, f says take whatever the input is and divide it by the input plus 1. So this would become x to the 10th power plus 3 divided by x to the 10th power plus 3 plus 1. Right, where, just to highlight this, this is the input of the f function. So it's got to be the input over the input plus 1. So that would be f composed with h composed with g evaluated at x. We can also have the composition of the same letter. So we could have something that looks like this, f composed with f evaluated at x. This is f evaluated at f of x, right? Where the f of x is equal to, where the f is being evaluated at x over x plus 1, right? It's always the input divided by the input plus 1. But now this other f is going to be the same thing. They want you to have the input, which is this guy. Here's the input, divided by the input plus 1. Right? So here is my input, and it's the input divided by the input plus 1. That's what the author did for the first one, same thing as I did. So far we have used compositions to build complicated functions from simpler ones, but in calculus it's useful to be able to decompose a complicated function into simpler ones, as shown in the following example. Okay, so here we have an example where we have the output, the final product of a composition of functions. Capital F is made up of lowercase f composed with g. So find those two functions that make this work. Okay, so lots of different answers to this. At heart, what does f of x mean? F of x means this, x plus 9. We're going to take an input. Here's my input. And what are we going to do to the input? We're going to add 9 to the input. Add 9 to the input. And then take the fourth root of this, right? Take the fourth root of the output in step 1. Right? So first add 9 to the input, then take the fourth root of the result. So as long as we do those two things, we can break it up into pieces. We can find two pieces such that when we compose these two functions in this order, we end up with this. So it might take a bit of a guessing and checking, but one super easy, obvious way is to look at it this way. So capital F of x is equal to f composed with g of x. So that means it's equal to f evaluated at g of x. So one obvious thing we could do is to define f of x to be equal to the inside part of the root, which would be the x plus 9. And the f would then be the outside part, which would be the fourth root. The fourth root of x, right? If we continue this example, this would mean that this is f of, and then we input an x plus 9 into there. And then the lowercase f means take the fourth root of your input. That would be equal to the fourth root of x plus 9. So this is one example that would work out, but it's not necessarily the only one. We can also look at it a slightly different way. How about, okay, so capital F of x is equal to f composed with g evaluated at x is equal to f evaluated at g of x. How about if we break it up? We have to do two steps, add 9 and then take the fourth root, but we can do it in pieces. How about if the g of x doesn't add all of the values, maybe it's just x plus 5. So I'm going to do part of the work there. And now the f of x function is the fourth root of x plus 4. So that when I input that into there, I'll get the desired result, right? So then this would be f of, this is x plus 5. And now if I input that into there, I'll get what I want. So now the f would be the fourth root of the input plus 4. And that input is this x plus 5. Right, so here is the input. And then if f is defined this way, it's going to be the input plus 4, and then take the fourth root of that. So we get that. So that's another way to do it. Let's think of another way to do it. All right, let's try one more and see if we can get more creative. If we have f of x equal to f composed with g evaluated at x, which is f evaluated at g of x. Let's have a case where the g of x gets you most of the way there. So maybe it's equal to the x plus 9. And in fact, it's also equal to the square root of that, which we know is equal to x plus 9 to the power of 1/2. And then the f of x is also equal to the square root of x, which is also equal to x to the power of 1/2. So when we come back over here, this is going to be f of, and then this is going to be this guy. So this will be equal to the square root of x plus 9. And then when we plug that into this guy, this will be equal to the square root of x plus 9, which is equal to x plus 9 to the power of 1/2. And then the outer is also equal to the power of 1/2. Remember that this notation of this is the same thing as raising it to the power of 1/2. And we do it once from the outside one. We do it again for this inside one. So that's what this one is equal to 1/2. And then those guys simplified to just give me x plus 9 to the power of 1/2 times 1/2, which is equal to x plus 9 to the power of 1/4, which is exactly what we wanted, the 4th root of x plus 9. Okay, so there is an obvious way to break this down. Let this inside part here, this guy, let that be the g of x function. That's one way to do it. And then let this outside part, this 4th root, this guy, be the f of x function. That way their composition gives you exactly what we want. That's one way to do it. But it's not the only way to do it. We can also break it down this way or this way. So there's really an infinite number of ways that we could do it. But usually there's one or two really obvious, easy ways to do it. Okay, hopefully that made sense. Okay, so here's one. This is that first way of doing it, that sort of obvious way. All right, now let's look at an example with an application, so applications of compositions. A ship is traveling at 20 miles per hour parallel to a straight shoreline. The ship is 5 miles from shore. It passes a lighthouse at noon. A. Express the distance s between the lighthouse and the ship as a function of d, the distance the ship has traveled since noon. That is, find f so that s equals to f of d. B. Express d as a function of t, the time elapsed since noon. That is, find g so that d equals to g of t. And finally, find f composed with g. What does this function represent? Okay, so here's a nice little picture to depict this question. Okay, so we have the ship right here, and it's traveling in this direction along a distance d, which is parallel to the shoreline. And then perpendicular here, we have a distance of 5 miles. So the boat is 5 miles from the shoreline, and it goes in this direction. Okay, and now we're looking at s, the distance between the lighthouse and the boat. So at this point, right at noon, it's going to be exactly 5 miles from the lighthouse. And then as the boat continues to travel along this direction, it's traveling a distance d at time t, so t hours later, right? So this is all in well, it didn't specify, but for convenience, it seems that we should make all the units match, right? They didn't say not to make them match, so why not? The ship is traveling at 20 miles per hour, so why not make the units miles for distance? So we'll say distance. Distances are going to be in miles. And time is going to be in hours. Okay, so distance d traveled. Okay, so express the distance s between the lighthouse and the ship as a function of d. Okay, so let me zoom out a little bit. Capture the whole thing. So express the distance s between the lighthouse and the ship as a function of d. Okay, well, luckily, because this is a nice right triangle right over here, right? This is a perfect right triangle. That's what this little notation there means. Then we know that s squared is equal to d squared plus 5 squared. Right? Pythagorean theorem tells us that s squared is equal to d squared plus 5 squared, or just 25. S squared equals to d squared plus 25. So if we want to solve for s, we can take the square root of both sides, square root of this side, square root of that side. Of course, that introduces a plus or minus. And so we have that s equals to plus or minus the square root of d squared plus 25. Now, we get to automatically ignore, right? I'll just say ignore the minus because s is a distance. It can't be a negative, right? So we ignore the negative. Ignore the negative. It doesn't make sense in the terms of this word problem for us to have a negative distance. So it's just going to be equal to the square root of that. So s equals the square root of d squared plus 25. Okay, so I think that's part A. Express the distance s between the lighthouse and the ship as a function of d. The distance of the ship has traveled since noon. That is, find f so that s equals to f of d. Okay, so s, that distance s, now can be described as a function f of d, right, where the input is d, and that's equal to the square root of d squared plus 25. So that takes care of A. Now let's look at B. Express D as a function of t, the time elapsed since noon. Okay, well that one's extra easy. So we are told that the ship is traveling at 20 miles per hour. So the speed of the boat is equal to 20 miles per hour. 20 miles per hour. So if he travels for a time t at 20 miles per hour, his whole distance is going to be equal to the product of those two, d time, the speed times the time. So that must mean that the distance traveled is equal to speed times time. And time is just t, right? Given some t in hours. Like if he travels 1 hour, it'll be 20 miles. If he travels for 2 hours, it'll be 40 miles. And this guy is going to be 20. So we're saying g, which is equal to d, is equal to 20 times t, or just 20t. And finally, find c, which is f composed with g, and express what that represents. So part C is that f composed with g is going to be equal to, let's pause for a second there and see what the variable is. And this is equal to f evaluated at g of, well, we have a g of t here, right? Oh, I should have clarified that over here. So this is going to be medium. This is g of t, which is the d, and that equals to that. So this is going to be g of t, plug in a t, right? So that's got to be a t there, t, and then this output is going to be some distance, d, and then that d is the one that goes there. Good. Okay, so then this is equal to the square root of g of t squared plus 25, which is then in turn equal to 20t squared plus 25. So then this is going to be equal to t squared times 20 squared plus 25. which we can then simplify a little bit. We can factor out, there's a 4 and a 5 here. So this is the same thing as t squared times 4 squared times 5 squared plus 25, or 5 squared. Inside that radical, which then just gives you 5 on the outside, square root of, and there's a 16t squared plus 1. And I believe that that's as good as it gets. We really can't reduce it any further. So that's our final result for the composition of the functions. So this is, make some space here. This is f composed with g of t. F composed with g of t. Finally, f composed with g of t. It's that guy. Okay, so what did we get? Okay, so for part A, we were able to find a function that described the distance from the lighthouse to the boat as a function of the distance it had traveled horizontally, right? So you give me that distance, right? The input was the distance traveled, and the output was the value of x, the distance to the lighthouse. For part B, we found a new function, g of t, where the input is the time, how long have you been traveling, and then the output was the distance traveled along the path of the boat here, the distance traveled. And finally, for C, we found this new composition of functions where the input is time, you tell me how long you've been traveling, and the output is going to be the distance from the lighthouse to the boat, right? This is going to be S. The input is T, the output is S, the distance from the lighthouse to the boat. Let's see what the author did. Okay, we can write distance S by the Pythagorean theorem. Okay, so d squared, that's the same thing I got since the ship is traveling. Yep, same thing. Same thing, except I simplified this by factoring out this a little bit more, but you could just leave it like that as well. It gives the distance the ship from the lighthouse as a function of time. Okay, good. So that should be enough to be able to work on your homework from this section. Let me know if you have any questions.